Hello, in this lecture 1, we will cover three-phase induction motor operation. To understand this, the prerequisites are construction of three-phase induction motor, working principle, torque equation, concept of slip and speed, power stages, power losses and efficiency, relationship between rotor copper loss, rotor power input and gross mechanical power developed. And we have already covered it in previous unit. The contents that we'll cover in this lecture 1 are the starters for squirrel cage and phase wound or slip ring induction motors. To understand the starters, the prerequisites are construction of three-phase induction motor, torque equation, relationship between rotor copper loss and rotor power input, and the second topic that we'll cover is the speed control mechanism. To understand the different speed control methods of three-phase induction motor, the prerequisites are the concept of slip, speed, relationship between speed, slip, frequency, number of poles and applied voltage. And the starter for slip ring induction motor or phase wound induction motor is the rotor resistance starter. So to understand the concept of this rotor resistance starter, the construction of the slip ring induction motor should also be known to us. So after completing these contents, we all will be able to describe the necessity of the starters, types of starters with connection diagram, and also we will be able to explain and apply the different methods of speed control of three-phase induction motor. So first we'll see the starters. So the probable questions that may be asked on the starters are: why the current is high at starting in induction motors? Describe with neat diagram the working of dual starter of induction motor. What are different methods of starting induction motors? Explain the significance of each. List the different methods of starting an induction motor and explain any two with neat diagram and protective devices. Justify that at starting the star connected stator winding causes the reduction in voltage applied across the stator windings. Now when the starter comes, the one question arises in our mind, that what is the necessity of the starters? That we have already discussed in DC motor, that at starting for a fraction of second the speed is 0, right, and hence the back EMF becomes 0. Due to 0 back EMF, the current drawn by the motor is 6 to 12 times the rated current. Why? Because the armature resistance value is very low and that may be neglected, and the applied voltage is of suppose 230 volts, so that may raise the starting current to 6 to 12 times the rated current. So to limit this inrush of current at starting, a variable resistance is connected in series with the armature winding, and that is nothing but the starting resistance and is known as the starter. Similarly, the three-phase induction motor at starting takes 5 to 7 times the rated current, and this initial inrush of current drops the line voltage, due to which the operation of electrical equipment connected to the same lines gets affected. Hence, to limit the starting current, the starters are used. Now we'll see in squirrel cage and slip ring induction motor how the starters are used. In squirrel cage induction motor, we know that at starting when the rotor conductors are stationary, the rotor is just like a short circuited transformer secondary. I think you know that. We already studied in construction of induction motors. Therefore, the current drawn by the rotor will be very high, and stator will be drawing a high current from the supply line. So this current is for a fraction of a second and decreases as the motor picks up the speed. This will affect the performance of the motor as well as the equipment connected to the same lines. The magnitude of this current is determined by the electrical design and not by the mechanical load on the motor. So these are the concepts related to the design of electrical machines, and that we'll cover in electrical machine design course. The starting current can be limited by adding external resistance in the rotor circuit. and hence the torque can also be improved. Addition of external resistance in the rotor circuit is possible in case of slip ring induction motors only. Why? Because we know that by using the variable resistance we can add the external resistance in series with the rotor winding of slip ring induction motor, but it is not possible in squirrel cage induction motor. Why? Because the rotor bars are short circuited at both the ends by using end rings, right? So the starting of squirrel cage induction motor is possible by applying reduced voltage to the stator winding. The reduced voltage applied to the stator winding reduces the heavy current and hence controls the starting high current. Once the motor reaches to the normal speed, the full voltage can then be applied. So now we'll see the different starting methods for squirrel cage and slip ring induction motors, and that are as follows. So for squirrel cage induction motor, the different starters used are direct online starter, that is dual starter, primary resistor starter, auto transformer starting, star delta starter, and for slip ring induction motor, the starter is rotor resistance starter. So first we'll study the starters for squirrel cage induction motor. So first starter for squirrel cage induction motor is direct online starter. Right, so by observing this diagram, it is clear that in this method of starting, the supply is directly given to the induction motor. That's why it is also known as direct switching or full voltage starting. So in this case, as the full voltage is to be applied, the motor may get damaged due to the high rate of temperature rise and large starting current. The reason for high temperature rise and large starting period are large drop in supply voltage, heavy load on motor, and rotor resistance may not be sufficient to limit the starting current. The starting high current presents for a fraction of a second during starting, as induction motor starting torque is about twice the full load torque. That we have already discussed in torque speed characteristics and torque speed characteristics of three-phase induction motor. Right? Now we'll see the derivation for the developed starting torque by direct loading. And we know that how the power input to the rotor can be calculated. That is by using the product of omega and the torque developed. So the omega is given by what? 2 pi ns by 60 and torque T. So the power input to the rotor is 2 pi ns T by 60 and the rotor copper loss is given by S times the power input to the rotor. And the rotor copper loss is given by the square of the rotor current I2 and the rotor resistance R2, and that is equals to S multiplied by 2 pi NST by 60. So here we can take this 2 pi ns by 60 as constant, so we can write it as I2 square R2 is equals to SKT, where K is what? Constant. So the torque developed is given by the equation 3 I2 square R2 by Ks. So we can take that torque is directly proportional to the square of the rotor current I2 and inversely proportional to the slip S, and that is for constant values of rotor resistance R2. And we know that rotor current is due to the stator current. That's why I2 can be directly proportional to I1. Therefore, torque is directly proportional to the square of the stator current I1 and inversely proportional to the slip S. Therefore, T is equal to K1 I1 square by slip, where K1 is what? Another constant. So therefore, at starting slip, that is S is equals to 1, starting torque is equals to K1 IST whole square. At full load, the S can be represented at SF. Therefore, the full load torque TF is equals to K1 IF square by SF, where IF is what? Full load current and SF is the full load slip. So the ratio of the starting torque to the full load torque can be given as the square of the ratio of starting current to the full load current multiplied by the full load slip. Therefore, the starting torque is equals to the full load torque multiplied by the square of the ratio of starting current to the full load current multiplied by the full load slip. So when the motor is directly connected to the supply system, the starting current becomes equal to the short circuit current. So we can write that starting current is equal to the short circuit current ISC. Therefore, the starting torque can be given as full load torque multiplied by the square of the ratio of short circuit current to the full load current multiplied by the full load slip. Now the second starter is the primary resistor starting. This primary resistor starting is also for squirrel cage induction motor, and the squirrel cage induction motor, the starting current can be controlled by using a reduced voltage. So by applying a reduced voltage to the stator winding, the starting current can be controlled. So to control the starting current, a reduced voltage can be applied to the stator winding of induction motor by connecting variable resistors in series with each stator winding. So at starting, when the supply is switched on, the resistance value causes the voltage drop in resistors, which further causes the reduction in voltage applied across the stator windings. The resistance is cut out in steps as the speed of the motor increases and finally short-circuited as the motor attains the normal speed. Right? So that's why this method is very simple and provides smooth acceleration, as only the variable resistors are required for the starting. So when the applied voltage gets reduced due to the series connected resistors, the flux is reduced. Right? Why? Because we know that the flux is due to the current flowing through the rotor conductors, right? And this reduced flux causes reduction in rotor induced EMF and hence the rotor current. If the starter reduces the applied voltage V to kV, the starting current also gets reduced in the same proportion, that is IST is equals to K times ISC. What is ISC? ISC is the short circuit current. Therefore, the starting torque in primary resistor starting is equals to the full load torque multiplied by the square of the ratio of starting current to the full load current multiplied by full load slip. And by solving this, we will get that starting torque using primary resistor starting method is equal to K square times the torque developed by direct online starter. So this is the diagram for primary resistor starter. So here you can see that the resistors, that is starting resistance, which are the variable resistance, are connected directly in series with each stator winding, right? So when the voltage is to be applied, that gets reduced. So the reduced voltage can be applied to control the starting current in squirrel cage induction motor, right? So this is the one method to control the starting current in squirrel cage induction motor. Now the next starter is auto transformer starting. So in this method also, to control the starting current, a reduced voltage can be applied to the stator winding of induction motor by connecting 3-phase auto transformer tappings with suitable number of turns in series with each stator winding. We know that in auto transformer there are different tappings, right? And the tappings are what? The suitable number of turns can be selected. So by using the suitable number of turns, we can select the suitable voltage. Means what? We can reduce the applied voltage. So this method is very simple as the voltage is reduced by transformation, and therefore the current and power taken from the source also gets reduced. Hence the internal losses are small for the starting grid. So therefore at starting, when the supply is switched on, the tapping at suitable points of 3-phase auto transformer causes the reduction in voltage applied across the stator windings. and therefore the number of turns is cut out in steps as the speed of the motor increases. And finally, full supply voltage is applied as the motor attains the normal speed. If the starter reduces the applied voltage V to kV holds, the starting current also gets reduced in the same proportion. That we can write that starting current is equals to K times the short circuit current. What is K? K is the transformation ratio. Therefore, the starting torque using auto transform starting is equals to full load torque multiplied by the square of the ratio of starting current to the full load current multiplied by the full load slip. So after deriving this, after arranging all the terms, again we will get that the starting torque by using auto transform starting is always equal to K square times the torque developed by direct online starting. This diagram explains that auto transformer with tappings is connected in series with the stator winding. So with suitable number of turns in series with each stator winding, a reduced voltage can be applied to control the starting current in squirrel cage induction motor. On the next starter is the star delta starter. In this method also, to control the starting current, and reduced voltage can be applied to the stator winding of induction motor by connecting stator winding in star across the supply mains during starting period, and then in delta across the same supply voltage during running condition. So this method is cheap, simple, as the voltage is reduced by star delta connection and therefore no power loss. Hence this method is effective and efficient. At starting, when the supply is switched on, the star connected stator winding causes the reduction in voltage applied across the stator windings. The voltage across the star connected stator winding is 1 by root 3 times the line to line voltage. As we know that in star connection, the relationship between the line voltage and the phase voltage is that the line voltage is equals to root 3 times the phase voltage. Therefore, the applied voltage gets reduced by 57.7%. So after a fraction of a second, as the speed of the motor increases and finally reaches the normal speed, the stator winding is connected in delta. The delta connected winding, as shown in figure, will have the full voltage and normal current flows through the winding. Hence, to understand how the reduced voltage can be applied to the stator winding at starting using star connection, and how the full voltage can be applied to the motor during running condition using delta connection, the relationship between the phase current, line current, and the phase voltage and line voltage is useful. The concept of star and delta connection is used here. So as we can see here, in delta connection, the line current is root 3 times the phase current. So the current flowing through this line is the line current, and the line voltage, the voltage between these two lines, is the line voltage. So this line voltage is equals to the phase voltage, that is the voltage across these two phases, these 2 points. So therefore the phase current is equals to the ratio of the applied voltage to the impedance, and the line current is root 3 times this phase current. So root 3 multiplied by the ratio of the applied voltage to the impedance. In star connection, we can see that the line voltage is equal to the root 3 times the phase voltage. That's why the phase voltage is equals to V by root 3, right? And the line current is equals to the phase current. So therefore in star connection, line current is equals to the phase current, and that is equals to V by root 3 multiplied by Z. So at starting, voltage across each phase winding is equals to what? 1 by root 3 times the line voltage, as shown in star connection above, right? So in star connection, the line and the phase values of current are equal. Therefore, starting current per phase is equals to 1 by root 3 equal to starting line current. Therefore, the starting current is equals to the short circuit current divided by root 3. Therefore, the starting torque by using star delta starting is equals to the full load torque multiplied by the square of the ratio of starting current to the full load current multiplied by the full load slip. And the final equation is 1 by 3 multiplied by full load torque multiplied by the square of the ratio of short circuit current to the full load current multiplied by the full load slip. Now the concept can be easily understood by using this diagram. So as you can see that here this stator winding is connected in star and in delta. So at starting, when the starting current is to be limited, the stator winding is to be connected in star. So this switch is switched over to this position. Now when the motor attains a normal speed, then the switch is switched over to this position and the stator winding can be connected in delta. So using this star and delta connection, by applying the reduced voltage to the stator winding at starting, the starting current can be controlled. Now the last starter is for slip ring induction motor, and that is the rotor resistance starter. So in this method also a full voltage is applied across the stator winding and variable resistance is connected in series with each phase of the rotor circuit. So as we have already discussed in construction of slip ring induction motor, that in slip ring induction motor it is easily possible to add external resistance in series with the rotor winding. That's why this starter is known as rotor resistance starter. So here the rotor resistance is nothing but the variable resistance, or we can say that is the starting resistance. So the external resistance added in the rotor circuit reduces the starting current and also improves the power factor. This causes an increase in the starting torque of the motor as well. The arrangement of brushes and slip rings is used to add the external resistance in the rotor circuit at the starting instant. The resistance is then cut out in steps during the acceleration and automatically short-circuited the rotor winding through slip rings by moving the meter collar along the shaft to run the motor at normal speed. Right. So using this diagram, it is easily clear that the stator winding is directly connected to the supply and the rotor winding is connected to this variable resistance using the slip rings and brush arrangement. So at starting, when the motor is to be started, the full resistance is connected in series with the rotor winding, right? So as the full resistance is connected in series with the rotor winding, the starting current can be controlled. And as the motor approaches to the normal speed, this variable resistance is cut in steps, and then finally it is zero when the motor rotates at the normal speed. Now the second topic that we'll cover in this lecture is the speed control of induction motor. As we have already covered in the first lecture of this induction motor, that synchronous speed can be calculated by the equation 120 F by P, where F is what? Frequency, P is the number of poles, right? Similarly, we have also discussed the slip, the concept of slip. That slip is nothing but what? The difference in speed of the field speed and rotor speed. And the slip S is given in fraction by the equation, the difference of synchronous speed and rotor speed divided by the synchronous speed. Therefore, the speed equation of induction motor becomes N is equals to N is what? Rotor speed, and that is equals to 120 F by P multiplied by 1 minus S. So from the above expression, it can be stated that the speed of induction motor can be controlled by varying the stator side factors and rotor side parameters. The different speed control methods are as follows. So from the stator side, as we have seen in the equation, by changing the number of poles, the speed of the induction motor can be controlled. By changing the supply frequency, the speed of the motor can also be changed. Then by varying the supply voltage, again the speed of the motor can be controlled. From the rotor side, there are two methods. By changing the resistance in the rotor circuit, as it is easily possible in slip ring induction motor, and by injecting an EMF in the rotor circuit, right? So these are the speed control methods or mechanisms of three-phase induction motor. So first method that we'll see is the speed control by changing the number of poles. So as we have already seen that the synchronous speed is equal to 120 F by P, right? So speed is inversely proportional to the number of poles. So this method is not possible with slip ring induction motor, as the rotor is wounded with winding and hence there is fixed number of rotor poles. The design could be complicated to produce the same number of poles of both the windings, but the squirrel cage induction motor is designed with short-circuited rotor bars and the rotor easily adapts itself to any number of stator poles. So from the equation N is equals to 120 F by P in bracket 1 minus S, it is also clear that the synchronous and rotor speed could also be changed by changing the number of stator poles. The change in number of poles of the stator is achieved by using the following methods, and that are multiple stator winding, independent windings on the rotor, pole amplitude modulation technique. Now the second speed control method is by varying the supply frequency. So the synchronous speed and the rotor speed of an induction motor can be controlled by varying the supply frequency as expressed by synchronous speed is equals to 120 F by P. So to vary the supply frequency is not easy, and the requirement of variable frequency power supply makes this method costlier. The variable frequency power supply with the auxiliary equipment increases the maintenance and decreases the efficiency, hence this method is rarely used. To maintain the constant flux in the air gap and hence the torque, and to operate the motor satisfactorily, the supply frequency and the supply voltage need to be changed proportionately. Now the third method is by variation of supply voltage. As the supply voltage is to be varied, that's why this method is simple, requires low maintenance and hence cheap. It has limited use due to the reasons as follows. A relatively small change in speed requires a large change in supply voltage. A large change in supply voltage causes large change in flux density and hence the motor operation is restricted by magnetic saturation. Limited speed ranges from rated speed to lower speeds. Reduced supply voltage results in the reduced torque and brings the motor to standstill. The next method is by variation of supply voltage, that is continued to the previous slide. So the equation for maximum torque is equal to K E2 square by twice X2. What is E2? E2 is the rotor induced EMF. What is X2? X2 is the rotor reactance. So similarly, the starting torque will be maximum when slip is maximum, that is S is equals to 1. At starting, the per phase values of rotor resistance and reactance becomes equal. It is also clear that the slip at maximum torque is independent of supply voltage. Therefore, the variation in supply voltage does not affect the synchronous speed. Speed control by changing the resistance in the rotor circuit, and this method is for slip ring induction motors only and not for squirrel cage induction motor. So the motor speed is controlled by adding an external resistance in the rotor circuit in a similar way to that of the armature rheostat control method of DC shunt motors. Therefore, we can say that there are some advantages of this method, and that are low operating efficiency due to the increased I2R losses with increase in rotor resistance. The setup of external resistance to be added in series with the rotor circuit is bulky and expensive. The speed depends upon the rotor resistance as well as upon the load on the motor. So for the low value of Sx2, when the rotor speed is nearly equal to the synchronous speed, the Sx2 is negligible as compared to the rotor resistance R2. The torque equation will be as follows. So the running torque is equals to Ks E2 square by R2. What is R2? R2 is the rotor resistance. As the rotor induced EMF E2 is constant, the torque T is proportional to the slip S and inversely proportional to the rotor resistance R2. Hence, for a constant torque, the speed can be reduced or slip can be increased by increasing the rotor resistance R2. So this method of speed control is used for variable torque load where the speed drops with respect to the drop in torque. The example is fan load. It is used for short or intermittent operation. Examples are low power motor and overhead cranes. So it is easily explained by using this diagram that this variable resistance is to be added to the rotor circuit by using the slip rings to control the speed of the induction motor. The stator winding is directly connected to the supply using this switch and fuse. Now the second method for the speed control is by injecting an EMF in the rotor circuit. In slip ring induction motor, by adding external resistance in the rotor circuit, the motor speed can be controlled. In a similar way, the speed of an induction motor is controlled by injecting an EMF in the rotor circuit. The rotor frequency is slip S times the fundamental frequency that we already studied in the lecture. Therefore, it is necessary to inject the voltage of the same frequency as the slip frequency. So the F dash should be equals to S times the supply frequency, right? And that is known as slip frequency. The voltage can be injected in phase or phase opposition to the EMF induced in the rotor. So injecting a voltage which is in phase with the EMF induced in the rotor results in lowering the rotor resistance. Injecting a voltage which is in phase opposition with the EMF induced in the rotor results in increasing the rotor resistance. So try to understand the concept here. So injecting a voltage which is in phase with the induced EMF in the rotor circuit will result in lowering the rotor resistance. But injecting a voltage which is in phase opposition with the EMF induced in the rotor will result in increasing the rotor resistance, right? So this is the concept how to inject an EMF in the rotor circuit, that is in phase and in phase opposition.